rise value on a transformer nameplate refers to the maximum allowable temperature rise of the transformer windings above the ambient temperature. It is typically expressed in degrees Celsius. As an electrical current flows through a transformer winding, it causes heat dissipation due to resistance, also known as copper losses. This heat can cause the temperature of the windings to rise. The rise value indicates the maximum permissible temperature increase of the transformer windings under normal operating conditions while ensuring that the insulation remains intact and the transformer's performance is not compromised. A 150 degrees Celsius designation on a nameplate means that the transformer windings are rated to withstand a maximum temperature rise of 150 degrees Celsius above the ambient temperature. The rise value is not directly related to impedance or voltage tolerance. However, it can indirectly affect these parameters. A higher temperature rise can increase the resistance of the windings, which in turn can increase the impedance of the transformer. If the transformer operates at a higher temperature than intended, the insulation materials may degrade prematurely, leading to reduced voltage tolerance. Therefore, it is important to ensure that the transformer is operating within its specified temperature rise limits to maintain its intended performance and safety. It's essential to understand the concept of ambient temperature in relation to transformer temperature rise. Ambient temperature refers to the temperature of the surrounding air or environment in which the transformer is operating. The transformer's nameplate temperature rise rating is based on a specific ambient temperature, typically around 40 degrees Celsius. If the actual ambient temperature exceeds this value, the transformer's load must be derated to prevent overheating. Derating involves reducing the load on the transformer to compensate for the higher ambient temperature. This ensures that the winding temperature does not exceed the maximum allowable temperature rise specified in the nameplate. Now, let's delve into the materials used for transformer insulation and how temperature affects their lifespan. Transformer windings are typically insulated with materials like paper, varnish, or synthetic resins. These materials have a maximum operating temperature. Exceeding this temperature can accelerate the degradation of the insulation, leading to premature failure of the transformer. The Arrhenius equation describes the relationship between temperature and the rate of chemical reactions, including the degradation of insulation materials. According to this equation, the lifespan of insulation is inversely proportional to the exponential of the temperature. This means that even a small increase in temperature can significantly reduce the lifespan of the insulation. Transformer manufacturers design transformers with specific insulation classes. These classes define the maximum allowable operating temperature for the insulation materials. Common insulation classes include A, E, B, F, and H, each with a different temperature rating. It's crucial to select a transformer with an insulation class appropriate for the operating environment to ensure long-term reliability. Cooling methods also play a significant role in managing transformer temperature. Transformers generate heat due to coal losses and copper losses in the windings. Effective cooling is essential to dissipate this heat and maintain the winding temperature within acceptable limits. Common cooling methods include natural air cooling, forced air cooling, oil natural cooling, and oil forced cooling. Natural air cooling relies on convection to dissipate heat from the transformer's surface. Forced air cooling uses fans to increase the airflow over the transformer, enhancing heat dissipation. Oil natural cooling involves immersing the transformer core and windings in oil, which acts as both an insulator and a coolant. The oil circulates naturally due to convection, transferring heat to the tank surface, where it is dissipated. Oil forced cooling uses pumps to circulate the oil through a radiator or heat exchanger, providing more effective cooling for high-capacity transformers. Transformer loading also directly impacts the temperature rise. The load on a transformer is the amount of current it is supplying to the connected equipment. As the load increases, the current flowing through the windings also increases, leading to higher copper losses and a greater temperature rise. It's important to operate the transformer within its rated capacity to avoid overloading, which can cause excessive temperature rise and premature failure. Overloading can occur due to several factors, including increased demand from connected equipment, voltage fluctuations, or harmonic currents. Monitoring the transformer's load and temperature is crucial to identify and prevent overloading. Protection devices such as overcurrent relays and thermal overload relays can be used to protect the transformer from damage due to overloading. Now consider the impact of harmonics on transformer temperature rise. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads, such as electronic devices and variable frequency drives. These harmonic currents can cause additional losses in the transformer, leading to increased temperature rise. Harmonic currents increase the root mean square current flowing through the windings, resulting in higher copper losses. They can also cause eddy current losses in the core, further contributing to the temperature rise. To mitigate the effects of harmonics, harmonic filters can be installed to reduce the harmonic content of the current. K-factor transformers are specifically designed to withstand the effects of harmonic currents. They have a high core and winding capacity to handle the increased losses caused by harmonics. Regular maintenance and inspection are essential for ensuring the proper operation and longevity of transformers. Maintenance activities should include inspecting the transformer for signs of damage, such as oil leaks, corrosion, or insulation degradation. Testing the insulation resistance of the windings can help identify potential insulation problems. Measuring the oil level and condition in oil-filled transformers is also important. Oil samples should be tested for properties such as dielectric strength, acidity, and water content. Maintaining proper ventilation around the transformer is crucial for effective cooling. Obstructions that restrict airflow should be removed to ensure adequate heat dissipation. Tightening loose connections can prevent overheating and potential fire hazards. Infrared thermography can be used to detect hotspots on the transformer, indicating potential problems such as loose connections or insulation failures. Transformer standards, such as those published by the Institute of Electrical and Electronics Engineers and the National Electrical Manufacturers Association, provide guidelines for the design, testing, and operation of transformers. These standards specify the allowable temperature rise limits for different types of transformers and insulation classes. They also outline the procedures for testing transformer performance and safety. Adhering to these standards helps ensure that transformers are designed and operated safely and reliably. Let's look into the different types of transformer temperature rise tests. Temperature rise tests are conducted to verify that the transformer's temperature rise does not exceed the limit specified on the nameplate. These tests are typically performed at the manufacturer's facility before the transformer is shipped. The transformer is energized and loaded to its rated capacity, and the winding temperature is monitored using thermocouples or resistance temperature detectors. The test is continued until the temperature stabilizes, indicating that the transformer has reached its maximum operating temperature. The temperature rise is calculated by subtracting the ambient temperature from the winding temperature. If the temperature rise exceeds the specified limits, the transformer design may need to be modified to improve its cooling performance. Now consider the economic implications of transformer temperature rise. Operating a transformer at excessive temperatures can lead to premature failure, resulting in costly downtime and replacement expenses. Proper transformer cooling and maintenance can extend the lifespan of the transformer, reducing the total cost of ownership. Selecting energy-efficient transformers can also help reduce operating costs by minimizing losses and improving overall system efficiency. Investing in transformer monitoring systems can provide valuable data for optimizing transformer performance and preventing costly failures. Furthermore, let's talk about the environmental considerations related to transformer temperature. Overheating transformers can contribute to increased energy consumption and greenhouse gas emissions. By operating transformers at optimal temperatures, energy waste can be minimized, reducing the environmental impact. Using environmentally friendly transformer oil can also help reduce the environmental impact of transformer operation. Proper disposal of used transformer oil is essential to prevent contamination of soil and water. Regulations regarding transformer disposal and recycling should be followed to ensure responsible environmental stewardship. Now consider specific applications where transformer temperature rise is critical. In data centers, where continuous operation is essential, transformer temperature rise must be carefully managed to prevent downtime and data loss. In industrial facilities, where transformers supply power to critical equipment, overheating can lead to production disruptions and safety hazards. In renewable energy systems, such as solar and wind farms, transformers play a crucial role in connecting the renewable energy source to the grid. Proper temperature management is essential for ensuring the reliability and efficiency of these systems. In transportation systems, such as electric trains and subways, transformers are used to supply power to the traction motors. Overheating can lead to service disruptions and safety risks. Understanding the specific requirements of each application is crucial for selecting and operating transformers safely and reliably. Finally, let's discuss future trends in transformer temperature management. Advances in materials science are leading to the development of new insulation materials with higher temperature ratings and improved thermal conductivity. Smart transformers with built-in monitoring and control capabilities are becoming increasingly popular. These transformers can automatically adjust their cooling performance based on real-time operating conditions. The use of computational fluid dynamic simulation is enabling engineers to design more efficient transformer cooling systems. The development of new cooling technologies, such as nanofluids and microchannel heat exchangers, is paving the way for smaller, more efficient transformers. As technology continues to advance, transformer temperature management will become even more sophisticated, leading to improved reliability, efficiency, and sustainability. Understanding the factors influencing transformer temperature rise is crucial for ensuring the safe and reliable operation of electrical power systems. By implementing proper cooling, maintenance, and monitoring practices, the lifespan of transformers can be extended, reducing costs and minimizing environmental impact. Remember to always consult with qualified electrical professionals when working with transformers. Their expertise is essential for ensuring safe and effective operation. This comprehensive overview should provide a solid understanding of transformer temperature rise. Understanding the rise value on a transformer is essential for determining its maximum operating temperature and ensuring its longevity. It is critical to consider the ambient temperature, insulation class, cooling method, and loading conditions to prevent overheating and premature failure. By following best practices for transformer operation and maintenance, you can maximize the reliability and efficiency of your electrical power system. Remember that while the impedance and voltage tolerance are not directly related to rise value, the rise value can have an indirect effect on these parameters. So, maintain your transformers properly for reliable service.